Hi everyone, welcome back to another math video. Today we will be going over question 4 from the 2020 Fire Math Competition. The question defines an m by n grid as a grid that has m rows and n columns. Each cell is colored either red or blue. Part A of the question asks, how many different ways can we color a 5 by 1 grid such that 3 cells are red and 2 cells are blue? Since a cell can only either be red or blue, we can just do 5 choose 3 to find the number of red cells, and the blue cells will just follow. This works out to be 5 factorial over 3 factorial times 5 minus 2 factorial. If we work this out, we'll get 5 times 4 times 3 times 2 times 1. Over 3 times 2 times 1, and this is 3 factorial. We can cancel out these, and then we're left with 5 times 4 over 3 times 2 times 1. Calculating this out, we see that this equals 10 different ways. Part B of the question asks us to consider all the possible colorings of a 1 by 13 grid. It asks us to count the number of cells colored red and the number of cells colored blue for each possibility. It then asks us to list the maximum of each pair of numbers. What is the smallest number in the list? For this question, there are only 13 different colorings, so we can just write down all the different possibilities. We can write a chart with red on the left and blue on the right. For each possible grid, the number of red cells and the number of blue cells have to add up to 13. So we can just try out all the different possibilities. The first possibility, we can have 0 red cells and 13 blue cells. Or we can have 1 red cell, 12 blue cells, and it just keeps going. Next, what we do is to consider each pair of numbers. For each pair, we just list down the maximum of the two. So for the first one, it'd be 13. For the second one, it'd be 12. And we can just keep listing. Once we get to here, we have to be careful because now 7 is the maximum digit. So this is a list that we need to consider. Now what the question asks us to do is to find the smallest number in this list. And very clearly we can see it's 7. So our final answer will be 7. Part C asks us the smallest value of n, such that no matter how a 3 by n grid is colored, there must be at least 2 columns colored the same way. For this question, we have to make use of the pigeonhole principle. So, first we have to consider each column. Each cell in a column can be either red or blue, so there are 2 different possibilities. By the fundamental principle of counting, the total number of possible columns needs to be 2 times 2 times 2, which is 8. Now for the pigeonhole principle. It states that if you have n plus 1 pigeons, and you try to stuff them into n holes, then there necessarily will have to be at least 1 pigeonhole with 2 or more pigeons. So by the pigeonhole principle, if we have 9 columns and only 8 ways to arrange each column, then at least 2 columns will have the same arrangement. So our final answer is 9. Part D asks us to consider a 5 by 41 grid. It asks us to either prove or disprove that we can always find 3 rows or columns such that the 9 cells in the intersections are all the same color. First, we call a column red heavy if it has 3 or more red cells, and blue heavy if it has 3 or more blue cells. For example, if we have a column that is red, red, blue, red, blue, then this column will be red heavy. If we have a column like blue, blue, red, then this column is blue heavy. Without loss of generality, we can say that since there are an odd number of columns, there are more red heavy columns than blue heavy columns. This means that the number of red heavy columns must be greater than 21. For the hypothesis in the question to be true, we need to prove that at least 3 columns will have the same arrangement of cells. Using combinatorics, we find that there are 5 choose 3 plus 5 choose 4 plus 5 choose 5 ways to arrange a column such that there are more red cells than blue cells. This is equal to 10 plus 5 plus 1, which is 16 different arrangements. However, we come to the realization that a red column with 4 or 5 cells is just a column with 3 cells with an extra red cell. For example, a column of 4 red cells like red, 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 blue can just be treated as red, 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 blue, blue. If we take this to be true, then now there are only 5 choose 3 ways to make a column where there are more red cells than blue cells. 5 choose 3 is equal to 10. Now we have to make use of the extended pigeonhole principle. So we have 21 or more columns that are red heavy. But only 10 arrangements. We have to have at least 3 columns that have the same arrangement of red cells. Thus, this proves our hypothesis.